For the next demonstration on the graph data structure, we're going to start taking a look at some graph algorithms, and we're going to start out with a depth-first traversal. Now, depth-first traversal requires a stack, so we're going to give ourselves a place to draw in our stack. We'll start from the bottom and work our way up from here. Now, the depth-first traversal in this case is going to start out at the vertex A. And the first thing that we're going to do is we're going to take the vertex A, we're going to push it onto the stack, we're going to visit it, and we're going to mark it as visited. Okay, now we take a look at the vertex at the top of the stack, A, and all of the vertices adjacent to it that haven't yet been visited. So that's B, D, and G. And we're going to visit the first of these in alphabetical order, which is B. So we take the vertex B, we push it onto the stack, we visit it, and we mark it as visited. And now we repeat the procedure. We take a look at the vertex at the top of the stack, B. We take a look at all of the adjacent unvisited vertices. Well, A has already been visited, so that just leaves E and F. We pick the one that's alphabetically least, in this case E, push it onto the stack, visit it, and mark it as visited. Now once again at the top of the stack we have E. We take a look at adjacent unvisited vertices. In this case, B is already visited. The only one we have is G. We push G onto the top of the stack. We visit G, and we mark G as visited. Now the vertex on the top of the stack is G. We find all adjacent unvisited vertices. Well, both A and E have already been visited, so that means that there's no place to go from G. We're going to pop it off the top of the stack, which takes us back to E. So notice we're kind of going backwards in our path. Now E also has no adjacent unvisited vertices, so we're going to pop it off the stack, which takes us back to B. Now from B, we've already visited A and E, so that leaves us with F. So the next vertex we're going to visit is going to be F. Push it onto the stack, visit it, mark it as visited. Now at the top of the stack we have F. If we take a look at F, we've already been to B, but we haven't been to either C or D. So we can visit the lowest of these alphabetically again, which is C, push it onto the stack, visit it, mark it as visited. Now C is on top of the stack, so we'll take a look at all of the vertices connected to C. C is connected to F, which we've already seen, but H we haven't visited yet. We push it, we visit it, mark it as visited. Now from H there's no place to go except back to C, but we've already been there, so we're going to pop H off the stack, which takes us back to C. Now there's no place new to go from C, so we'll pop it off the stack, which takes us back to F. Now from F there is a connection to a vertex we haven't visited yet, and that's D. So we can push D onto the stack, we can visit it, and we can mark D as visited. But at D, there's no place new to go, so we'll pop it off the stack, which takes us back to F. But from F, we've already been everywhere we can, so we're going to pop it off the stack, which takes us back to B. From B, there's no place new to go, so we'll pop it off the stack, which returns us to A. And since we've seen everything that's connected to A gets popped off the stack as well. Now our stack is empty, which means that our traversal is complete. For our next example, we're going to take a look at another graph algorithm, in this case, a breadth-first traversal. Now the major difference between a breadth-first traversal and a depth-first traversal is the use of a different supporting data structure, in this case, a queue. So we're going to keep track of vertices that we still have to visit using a queue. Just like the last time, we're going to start out at vertex A, So we're going to visit A and mark it as visited. Except the main difference is in this case, we're going to say that we're currently working on vertex A. Of all of the vertices connected to A alphabetically, the one that comes first is B. So we're going to visit B, mark it as visited, and add it to the queue. But we're not going to move to B. We're still at vertex A. So we're going to continue on from vertex A and take a look at the next vertex that's connected to it alphabetically, which is D. Mark it as visited, and add it to the queue. Again, we're not moving to D yet. We're still at vertex A, so we're going to take a look at any other vertices connected to A that we haven't yet seen, such as G. Mark it as visited, and NQG. Now we've already seen all the vertices connected to A, so there's nothing more to do with A. So we can finish off with A. And to see where to go next, we're going to turn to our queue. And we're going to pick the vertex on the head of the queue, which is B. We're going to dequeue vertex B and make that the vertex that we're currently exploring. From there, we're going to again take a look at all of the connected vertices, at least the ones we haven't already seen yet. Now we've been to A, but we haven't been to E or F. So again, going in alphabetical order, we're going to visit the vertex E, mark it as visited, and add it to the queue. But we're still at B, so we'll take a look at the next unvisited vertex from B, which is F. Visit it, mark it, queue it. No place new to go from B, so we're done with B. Next up on the queue is D. So we're going to dequeue D and explore all the vertices connected to D. Well, we've been to both A and F, so we have no place new to go from D. We're done with D. So we go back to the queue, which takes us to G. Now from G, there's also no place new to go. We've been to both A and E, so we're done with G. And now we can go back to the queue, which takes us to E. When we take a look at E, there's no place new to go from E either, so we're done with E. And we come back to the queue to decide where to go next. Well, F, the next vertex in our queue, does have a connected vertex that we haven't seen yet, C. So we visit C, mark it as visited, and add it to the queue. Nowhere else to go from F, so we're done with F. Now back to the queue to decide where to go next. Tells us to go to C. So we go to C, and we take a look at all the vertices connected to C. Well, we've been to F already, haven't been to H, so we visit H, mark it as visited, add it to the queue, and we're done with C. Now we go back to the queue, we see that H is at the head of the queue, we dequeue it, we take a look at everything connected to H, nothing new there, so we're done with H, and when we go back to the queue we see it's empty, which tells us that this traversal is complete.